You have a look at this line, right? And you compare it to what you already have. Now you'll notice it's almost identical to this line with one difference. There's no I1. Instead, it's this thing, okay? And the whole point of doing a recurrence relation is to get rid of all of these integrals that you don't know how to do until you get to an integral that you do know how to do. So let's evaluate I1. That's not so hard. You probably manage that one, but let's just do it together anyway. This is 1 minus 1 over x, okay? So we know what this becomes. That's an x, that's log x, from 1 to 2. So you evaluate it at 2 first. Then you evaluate it at 1. That's going to be 0. So that's where you get this, which is a bit of a sigh of relief. Okay. So then you substitute this value for I1 into this line, and then you just rearrange a little bit, and you'll get this. Okay. So in fact, I'll take a bit of a shortcut. I'll write it in here. 1 minus log 2. Okay. And you can see the sole difference between this line and this line is that these guys have swapped places. So he's gone there, and she's come over here. Okay, so far so good, right? Now, how do we then use that? So you can see what's happened. Now that I have this, I've shown it. Okay, what's on the left-hand side has nothing to do with any kind of integration at all, okay? But we're going to use integration to take advantage of it, which is really cool, actually. This is all number theory stuff, right? All whole numbers. That's what this notation implies, right? So when you look at this case, what did we say? 1 by 2 by that. 2 by 3 by 2 squared. Oops, 3. And so on, okay? This thing matches this, okay? But it's where n approaches infinity, okay? Because it goes on forever, right? So how do we do this, right? Now, you have to be really, really careful and very thoughtful about it. You've got to go all the way back to this original integral, okay? So this guy here, in fact, even I1, right? I'll put it back on the board. What does it look like, right? And you might have noticed there was an actual diagram, but it didn't explain very much about what was going on. Okay, so it's this with respect to x. Okay, here's my question. What is that thing? Okay, 1 minus 1 over x. What does it look like? I'll draw you a picture. Okay. You've got an asymptote here at x equals 0. And then you have an asymptote at, now as x approaches infinity, this becomes nothing. So you're approaching 1, aren't you? Okay, so I've got this asymptote up here, and because it's minus 1 over x, it's upside down from what a normal hyperbolic is. Okay, so you're getting this kind of shape.
Okay.
So far, so good? Okay, now this integral is only interested in a very particular spot, namely from 1 to 2. Okay, so the actual area is this. That's I1. Okay, but before we go any further on that, I want you to look very carefully at what this is and the particular characteristics it has, because it has some really useful and unusual characteristics. Okay, so in between 1 and 2, okay, we already know what this area is, right? But we don't just know the area; we know it's actually in a little box. Look at this. What did I say this vertical height was? This is y equals 1, right? So the horizontal distance here is 1. This vertical distance is 1, right? So if you like, you can picture this integral as being nestled within a rectangle, a square actually, that is 1 by 1 unit. Okay. Now think about that. If this is y equals 1 minus 1 over x, okay? At least in this area, right? If I then considered what would happen if I did this, if I say squared it, okay? Because the values here are nestled between 0 and 1, right? When you square numbers that are between 0 and 1, do they get bigger or smaller? They get smaller because they're all fractions, right? So a number like this, which might be say half, will become a quarter, right? So if I were to graph this, it would go like here, I'm guessing, right? And if I increase the power, it would go even lower. And they would, as this approaches infinity, it gets lower and lower and lower and lower, right? And so, exactly, it's approaching 0. Now, what do these correspond to? Well, these areas, these ever smaller areas, they are I1, I2, I3, I4, I5, I6. So they're shrinking and shrinking and shrinking, which is why this whole sum, all of these areas, will be equal to some limiting thing. Okay? So what have I established? Okay. First, I've said, look, I1, right? It's between 0 and 1. Okay. Is that all right? Because it's in this box. In fact, I don't even need to say that. I can know exactly what it's equal to, but suffice it. Right now, once you've got I1, because it's in this area, right, and because its values are between 0 and 1, I2, for instance, right, is going to be less than I1.
Yeah.
Right? And I3 will be less than that again, right? So more generally speaking, right, IN is going to be, I should have said IN plus 1, will be less than IN, right?
Yeah.
As this number gets bigger, the area gets smaller, it gets lower. Does that make sense? Okay, so therefore, right, I can conclude from all of this that not only is I1 less than 1, right? All of them will be less than 1.
Yep.
Does that make sense? So I've got IN is less than 1, right? Is in this boundary. But because IN plus 1 is even smaller than that, it'll be IN plus 1 in there. Okay? Are you happy with that?
Yep.
Now, why did I do that? The reason why I needed this particular integral, is because that's what I have to get rid of over here. Right? I have to eliminate this because I know what 1 is and I know what log 2 is, but I have no idea what this is. I need to be able to say something about it and its value. Right? Okay, so now I can come to my main line of argument and I can say I've established that 0 is less than IN plus 1, which is less than 1. But of course I don't have IN plus 1 here. I've got 1 over n plus 1 times that. So how do I get that here? I guess I divide everything by n plus 1. So that'll become still 0. Divide, right? And then divide. Okay, I'm almost there. I want to know what this thing is equal to. And I have this boundary and I have this boundary. But I'm considering n as n gets bigger and bigger and bigger, right? As n approaches infinity, in fact, right? So this thing's going to change. It's not just going to change though. It's going to get smaller. This is the squeeze law, right? If I take the limit as n approaches infinity of this, and take the limit as n approaches infinity of this, it should be less than the limit as n approaches infinity of this.
Yep.
Okay, so what happens to this guy as n approaches infinity? Answer, nothing. Right? This is what I'm actually trying to work out, which is why it's being squeezed. And what's it being squeezed between? Well, look at this. This will be 1 over 2, 3, 4, 5, a million. It's going to be 0.
So
There we go.
0.
Okay, so on the basis of this line, I say that the limit of this as n approaching 50 is 0. Okay? So therefore, I can get rid of my graph now because I've done my argument about the graph. Right? I can therefore say, on this line here, I'll say the limit as n approaches infinity of this sigma notation, right?
So you don't have to prove that is
This?
sigma.
No, I'm about to. I'm about to write that, right? So I'm appealing to this line because that's what this talks about, okay? And I've shown this. I showed it earlier, so I'm just going to keep on progressing. Now I take limits of both sides, right? Equals 1 minus log 2. That doesn't change. It has no. It's independent from n. Minus the limit as n approaches infinity of this guy, which I have just gone to all the effort with my inequality to show is 0, right? Oops, sorry, I meant to say all of this stuff in here, right? All of that, okay? Now this is, I'm now going to evaluate it. And the first term is this, right? And the next term is this, and I need 3 to get my pattern. And because I'm taking the limit as n approaches infinity, it just goes. have my 1 over log 2, and then I have this, which is nothing,
Yeah.
so I'm finished.